All right, good afternoon, friends. This is Miles Keogh. I'm the Director of Grants and Research at the National Association of Regulatory Utility Commissioners. It's Friday, it's lunchtime, so that means it's time for another brown bag broadcast. Today, we've got something good for you. We're going to be looking at ways to get more juice out of how we're using our coal-fired power plants. A lot of discussion has been underway, largely prompted by the big news of EPA's release of the final rule of the Clean Power Plan. The Clean Power Plan sets goals for the states to reduce their emissions, primarily of carbon dioxide. And to establish those goals, the EPA talked about a number of different factors that went into those calculations. And a big one, I won't get into the details of it because I think we've all had just about enough of hearing about these building blocks, but a big factor in this was the ability to make improvements at your emitting facilities. Especially, the calculation thought especially hard about heat rate improvements. So here's the context that we come into today's presentation with. There are some states out there, at least one springs pretty quickly to mind, that have legislation that's either been considered or passed that say that that the response to the Clean Power Plan has to either very much focus or be exclusively limited to the kinds of performance characteristics improvements that you can get at affected facilities. Basically, you got to get into the affected plants and have them produce less carbon. And the trick to carbon dioxide emissions from coal-fired power plants is it's not like sulfur emissions or NOx emissions where there are control technologies that you can put on the smokestacks. CO2 is a natural piece of combustion, and so there are some tricks to this that are more difficult. So if you're one of these states that really wants to focus on on-site improvements and affecting the emissions characteristics of the affected EGUs, it starts to get a little tricky when you start to think about what are the technical quiver that you can draw from for options to comply. So for me, I had, always assumed that just meant heat rate improvements. And the informal anecdata that I was getting from conversations was that heat rate improvements are great, but that on-site efficiency, these EGUs are already pretty heavily incentivized just by the economics of plant operation to be very efficient. So that there may be limitations to how far you could further exploit heat rate improvements. That's not to say that it's not there, but just that there may be a note of realism that needs to be injected into some of the more ambitious ideas about it. And another approach on this is carbon capture and storage, which is a great technology and which I hope we'll get to explore in another brown bag broadcast going forward. But it doesn't necessarily neatly plug into the existing coal-fired pulverized coal fleet. So there isn't a lot else out there. Enter today's panelist, David Farnsworth from Great River Energy, who I got to see this gentleman provide the presentation that we're going to see today at the subcommittee on clean coal carbon capture management at the New York NARUC meetings back in July. And this was an eye-opener. The technology that we're going to spend a lot of time talking about today, or the operational approach with the technology that we'll talk about today, has been largely used in North Dakota. And I told you we wouldn't talk all Clean Power Plan all the time on this stuff, but the release of the final rule, one of the things we've done is we've started to parse through who are the states that improved their position between the proposed rule and the final rule, and who are some of the states that kind of got dinged. And one state definitely sticks out as a state whose goals were made much more challenging. On a rate basis, this isn't final numbers or anything. This is just my cocktail napkin mathematics at work here. It looks like on a rate basis about a 44% decarbonization, and on a mass basis about a 30% decrease or increase in the challenge that's posed by the goal between the proposed rule and the final rule for North Dakota. So this dry finding technology that's been put into place in North Dakota is something that I think is a really interesting thing for us to explore. It's not a magic bullet, it's not a final answer, but if you're sitting in North Dakota and you're looking at some more challenging rules than before, certainly you are well motivated to look at every option before you, even if you're challenging the plan in court, even if you're doing other kinds of work. If you're putting together some sort of a response to the Clean Power Plan, you're going to want to look at everything. So I think today's conversation with David Farnsworth is going to be amazing. So let me start by putting David on the line. David, can we hear you?
Yeah, you can hear me fine. I can hear you, I should say.
Yep.
And if you can hear me, we're good.
David, I'm going to turn things over to you. When you want me to go to the next slide, just give me the word and we'll roll that way.
Okay, what I'm going to talk to you about is there's a word that was just mentioned in Miles's introduction, and that is the word dry finding. It's actually a trademark we put on this particular technology, which we developed over the last 15 years in our coal fleet up in North Dakota. And it's a combination of the word drying and refining, because the technology does both, and with very good results as far as emissions go, as well as improving plant efficiency. So this system, as mentioned on the title slide here, has been in operation since the end of 2009, so we're approaching 6 years now. So why don't you go ahead with the next slide. Just a little bit about what is dry finding. Dry finding is it's a fuel enhancement, if you want to call it that. It's a patented technology. We have 9 U.S. patents on it, on this technology. It utilizes waste heat and mechanical separation for drying and refining the coal. So we don't use process heat, and this is heat that is going to go up the stack or up the cooling towers. And as a result of that, it really, there's some very good economics that go along with this. And this technology is particularly applicable for low-rank coal, and I'll describe what that is. And dry finding can benefit a large part of the U.S. and even more so the world. And I'm also going to touch on the world because we're actually working overseas right now in introducing this technology, which will have big ramifications overseas. So basically, the main benefits of dry finding is that it's very cost effective, and I'll explain why. Significant reduction in pollutants, and I'll show you some actual data on that. It improves plant efficiency, which is, and lowers carbon intensity, which is key for all the existing fleet and those utilities that are looking to try to retain these, low cost, reliable, base load sources of generation. We'll be looking at everything they can do to go ahead and lower their carbon intensity as a result of the Clean Power Plan that's been introduced. Next slide. So it's good that we really put this in context about what's going on around the world. As you can see from this graph, and this is up to 2010, the situation has gotten a lot more lopsided since then. But you can see right now that in Asia, there's over 4 times the amount of consumption of coal as there is in North America right now. And that number continues to increase quite a bit. I'll show you another graph on that. And as a result of that, this situation with, if one is concerned with carbon, CO2 as a cause for global warming, that we have to look at this from a world context. And this is something that makes it very much one of the reasons why we're introducing this technology into Asia also. Next slide. So here's what's going on around the world. So we're very well aware of it in the context of whatever we do in the United States regarding the control of CO2 emissions will be of no benefit do we not go ahead and do something around the world. And you can see right now that the amount of CO2 emissions in the developing countries has been stable, you know, one could say maybe even a little bit low, but projected forward, it's still projected to be a wide, you know, a portion of our economy. And it's not going to go away anytime soon, but you can see what is going on currently, mainly in Asia, China and India, and other places overseas. A lot of coal plants are being built. A lot of coal plants are on the board. China for a while was building one per week. It's slowed down a little bit now, but plants are being designed for a lot of applications throughout much of the developing world. And as a result of that, this situation will continue to be with us, that we'll be looking for ways of going ahead and reducing pollutants around the world as a result of this. Next slide. The coal comes in a wide range, and just to mention, because I'm going to focus on low-rank coals, but in general, low-rank coals are coals that are lower in their carbon and energy content, but they're high in moisture, or higher in moisture. The lower you go, higher moisture, less heat content. And the harder coals are just the opposite. And you know, generally they fall under, I mean, you could start all the way over in peat, and then you have lignite, and you have subbituminous, which would be Powder River Basin coal. You have bituminous, and then anthracite. And the higher coals are very expensive, mainly used in metallurgical purposes, and the lower rank coals are the ones that are mainly used for power generation and cement manufacturing and other industrial uses. Next slide. So this is an old slide, but I think it's still very much reflective of what is going on, where low-ranked coal is. And this would be lignite and subbituminous coal in particular is what I focused on here. But this generally gives you an idea of where that coal is located. And the U.S. in the past has been referred to, and I guess one could still refer to it as kind of the OPEC of coal reserves around the world. And so it is very much a abundant and as a result a low-cost source of energy in the United States. But you can see there's other places where there's quite a bit of coal, low-rank coal, that is being utilized throughout the world and where the proven reserves are. Next slide. Now, for those of you who are regulators or even the states and looking at where your coal comes from, if you take a look at this graph of or map of the United States, the fields are shown in various colors there. So, for example, lignite would be kind of that brown tan colored, and you can see that's predominantly up in North Dakota, Texas, Louisiana, Mississippi, and but the red is Powder River Basin coal, and that's coming out of Wyoming and Montana. Very inexpensive coal because the reserves are so large, and it's very easy to mine that coal in open pit mines. And there were a number of plants throughout the country 20, 30 years ago that switched over to Powder River Basin from using higher quality coals in order to lower their sulfur content. Most of the other coals around the country have a higher sulfur content than Powder River Basin coal does. So part of it with this fuel switching was a strategy to not have to have the expensive scrubbers, but also it was a very cheap source of fuel. So as a result, there was a lot of switching over to Powder River Basin coal, which you could see in the red circles there. And then you see some of the other coals that are out there. The cost of Illinois coal, and particularly Appalachian coal, has become very expensive. And so actually what you're seeing going on in places like the Carolinas is fuel switching over to natural gas. But the low-rank coals continue to occupy a very large swath of the coal fleet that we have in the United States, which is a low-rank coal. Next slide. Now, just kind of what is the situation today. Coal, despite its predictions of its death have been greatly exaggerated in terms of it's going to be around for a long time. You can see right now, it currently, in 2014, was nearly 40% of our electrical generation. Nuclear has been fairly stable, around 19%. There are a couple of plants down in Georgia, Vogels 3 and 4, that are being built right now. Those are strong base load plants, but very, very expensive. The price tag on that is coming out to be quite high. And so the gap with all the environmental regulations, as a number of coal plants have come off line as a result of the MATS rules and other regulations, a lot of the smaller, older units have either been shut down or on the drawing boards to be shut down. Close to 60 gigawatts of coal. Coal just probably, I don't know, maybe 8 years ago or so was 52% of the mix. So you can see that it's dropped considerably. However, what has happened is these utilities have invested a considerable amount of money in those coal plants, usually the larger, newer ones, that they want to be part of their mix going forward. And so they have spent hundreds of millions of dollars to invest in these units on emissions equipment and other things to keep them alive. And because base load, renewable is not base load, it's an intermittent resource, and it's not, so from a reliability standpoint, it suffers, and we don't have any good storage technology right now that's affordable. So the base load really has been supplied by coal and nuclear, and natural gas has been filling in the gaps. And natural gas has also been used to help counteract the intermittency of renewables. And by the way, the renewables, which you see there at 12.9%, the vast majority of that is hydro. So solar is a very small slice. Wind is getting bigger, but still a fairly small slice. Okay, next slide. So what does dry finding have to do with what, well, I would want to put it this way. The Clean Power Plan is on everybody's mind today. It's on the mind of the regulators. It's on the mind of the utilities. And how in the world will we comply with this? And this slide is a little bit old based on the rule which just came out here this week. But the building block assumed here a 6% efficiency improvement on all the existing coal plants. And actually, there was some part of the rule that actually showed this, in some cases, a little bit less under the new rule, but based on the significant cuts I'm seeing in some states, I don't believe that's the case. But in any case, what we know is that efficiency improvement is being touted by the EPA as one of the critical components to the states to get them toward a reduced dependence on carbon fuel for their electrical source. So that is kind of what we're striving for here, is to get a 6% or better improvement. And by the way, 6% on a thermal unit is very, very difficult to get. And this, I'm going to mention to you on here why this is an important component. Dry finding, when we've looked at it, we've tested a lot of coals and we've evaluated some different plants. And in fact, we just met with a large engineering firm that did some modeling and they've confirmed it. But generally, we're getting, by implementing dry finding, a 2 to 5% heat rate improvement on most plants that have low-rank coals. And the important thing about it is that it's cost-effective. The retrofit cost compared to other emissions control technology that we've seen in the last 10 years, it's quite a bit lower. And not only that, it's one of the few technologies we're aware of that actually reduces your costs as opposed to going ahead and raising them as an emissions control type strategy. So, and I'll go ahead and I'll show you why that is. And then the other thing is it provides some significant benefits. We've seen significant lowering of mercury, SO2, and NOx emissions. And even for those plants that have committed and retrofitted very high-priced controls technologies, retrofitting it with dry fining will allow you to reduce your reagent costs and your maintenance costs on these systems, because you don't have to put so much into them, and you don't have to run them as hard. So anyway, so the benefit of the whole thing is it keeps the electrical rates, it helps to keep them affordable, and also at the same time giving you positive environmental results. Next slide. This is a EPRI document here, and they took a look at what kind of things could be done to improve heat rate. And third on the list here as most effective was low temperature fuel drying, the generic word for drying coal. And the other two that are up on top basically require you to tear down your old boiler and replace it with ultra supercritical boilers with exotic material, very, very expensive. So really at the top of the list for heat rate improvement, we're looking at coal drying, or in this case, we all call it dry fining, as one of the most effective ways of improving heat rate on these units that it can apply to. Next slide. So just, I won't dwell on this. We're not a large utility. Great River Energy is a utility that we're an investor, we're a G&T, so we're not an investor-owned utility. We supply power to about 2/3, as you can see here, of the state of Minnesota. Our base load units, which all use lignite, are up in the North Dakota. And because we are a member-owned utility, rates are very, very critical to our members. We cannot go and recover our costs on things by a rate case or anything like that. We basically, our members, it goes directly to them. So our members are very, very sensitive toward their rates, and as a result, we are. And as you can see here, they have some very low costs, considering it's most of our customers are rural in nature, so there's a lot of distance between customers, and so in order to make their rates as affordable as they are, we have to do a lot of extraordinary things to get there. And so that's just a little bit on who Great River Energy is. And the Coal Creek Station is the largest station in North Dakota. It's two 600 megawatt units, and we'll go on to the next slide there. And this is where dry fining has been installed. So Coal Creek Station was very typical of what I'll call the newer generation large plants that were built in the late 1970s and early 1980s. So they are fairly large in size, 2 by 600 megawatt natural circulation plant. We have the best heat rate out of all the plants in the state because of dry fining and other efficiency improvements we've made. You know, we've got overfired air for NOx control. We have low NOx burners. We have a mine mouth plant, so right off the side of this, off the left-hand side of this picture of this power plant are some large open pit coal mines, and the coal comes in directly. We have about a 50-year supply of coal sitting right there, lignite, so it's very inexpensive. However, it is lignite, and in this particular case, our coal is low BTU, 6200, and it's 38% water. And anyway, well, I'll go into that a little bit more. We were commissioned about the time as many of the other plants. We are base load. We are a low-cost producer. We run near the top most of the time, and we have scrubbers and precipitators. We are a zero discharge plant. We don't discharge any water to the environment, and our dry fining system went commercial in late 2009, and we've pushed over 33 million tons through the system. So anyway, that's kind of a little bit about background of the plant that was retrofitted. This is a picture here. If you look at it, you will see the steam or the water vapor coming off of a stack of one of our dryers. We have these stacks so you can see the amount of moisture coming off. This moisture does not contain particulates or any other pollutants. It's just strictly water vapor. And so this is what's coming off the dryers. So you can see visibly the water that is coming off. Now, the beauty of this system that we have is it's a low temperature system. Unlike anything else that is either proposed or been experimented with around the world, they use processed steam and they use higher temperatures. And that creates significant problems, particularly on what we call volatiles, organics and stuff that can get up there into the stack, but this and create fire hazards and other things. But this is a fairly low temperature system, atmospheric system, and so we don't use any exotic parts, high pressure parts. All of this is using waste heat that is drawing from two main sources. One is the heat that would go up the stack and the heat that would go up the cooling towers. And so we don't use any external heat. We don't use any processed steam coming off the plant or anything like that. This design is fairly simple. There's not a lot of moving parts, exotic things that make for large maintenance headaches or things that can result in some kind of catastrophic shutdown of the system. Next slide. So just this is just kind of the guts of the system. This is one of the dryers. At Coal Creek, where we have two units, two 600 megawatt units, we have 8 dryers. We have redundancy, so we can go down to 3 dryers on each unit. And so basically the system is maintained online, so we don't have to shut down to maintain it. And just kind of in a nutshell, going from left to right, the wet coal comes in, the natural coal that we get, and we feed it into this dryer. We have a mechanical separation system in the first stage that goes ahead and takes out a lot of the bad actors that contain pyretic sulfur as well as mercury and other things that we don't want that normally get burned in the boiler and get sent out to be treated after the boiler. And then what we have is we have a fluidizing air system that fluidizes this. So we pre-crushed the coal to a 1/4 inch minus size so it can fluidize. If you take a look in the dryers, and actually you can look in these dryers, we have little inspection windows, and it looks like a jacuzzi. It looks like water kind of moving across. So we put the coal in, and this fluidizing air causes it to lift and kind of slowly work its way off to the right-hand side. And the fluidizing air is preheated, so some of the heat is coming there. And then in the middle of this thing, what looks like a bunch of crates in there or whatever, that's actually a bunch of tubes, fin tubes in there that carry warm water that's being heated from waste heat from the plant. And so as this coal migrates across over the period of about 20 minutes residence time, it's getting dried out. And then that air goes up through a dust collector and then comes out the stack that you saw on the previous slide. And then the product coal, the product stream comes out and goes there. Now, the stuff that gets rejected on the left-hand side for further cleaning, we use another mechanical process. So roughly, because that coal does contain some good coal still, so what we do is we send it through another mechanical separation, and most of that coal then goes back in the product stream. So we reject about 0.5% of the coal coming in as waste, which would be the stuff we don't want anyway. Next slide. So the retrofit we did, we designed the thing. We had done a lot of testing with pilot. We had done pilot testing. We had actually got a DOE funding that helped us on the prototype, and with the agreement that if this was commercially viable, we'd pay it back, which we have. That money was about $13 million for initial prototype, as well as we used our own funds from our company. And then we went ahead and retrofitted the unit, actually put the drying system within the plant. We had a little bit of space. You can see all these big cranes on this picture. There's a cold drying building. We had like a 70-foot gap in between the fan room and the electrostatic precipitator. We built it. So it was a tough location to build in, but it worked for us. It just happened to be what we thought was a good location at the time. So we did this retrofit, and one of the important things here is we did not require any additional outage time to do this. So we did our tie-ins during our regularly scheduled outages, and so the availability of units was pretty good when we did it. And because our results we knew were going to be so good, we decided to build both units all at the same time, retrofit them both at the same time. Next slide. I'm just going to go through just a couple pictures during construction. Here you can see the actual dryer units going in between the fan room, boiler fan room, which is on the upper part, and then the electrostatic precipitator, which is in the lower part of this picture. Next slide. Here you can see some bag houses that would go above the dryers. These are sitting down on the ground. They were pre-assembled and lifted up into place after we were ready. Next slide. This is just a picture of what the dust collector or bag house, if you want to call it. I call it dust collector because it's really, that's what it's getting, is just some coal dust. This is looking at the gallery there. So this, we recover whatever dust comes up and then put that back out of the product stream. Next slide. Here we went ahead, and because this coal was drier and a little bit finer, we did something innovative where we used air-supported conveyors. So what you're seeing here is these are some of the conveyors, and the conveyors actually, you know, they've got drives on either side, on the end of them, but the actual belt itself rides on a cushion of air as opposed to a bunch of rollers. And so it's like an air hockey table. So it's just amazing that this little amount of air we have with this hole coming through a plenum can float this entire belt with a lot of coal on it. And but anyway, so in doing so, this is also kind of a seal thing, so we don't have much of a dusting or you know, explosion type hazards and that sort of thing. Next slide. Okay, now I'm going to show you some actual results, and this was after we put the system in service. So you can see the coal that is in the blue there. This is what the moisture level was in the coal when we mined it, and then the green there is what it was after it went through our drying system. Now, one of the important things about this dry finding system is that you can dry. There's a lot of variability and not variability, a lot of control here. We can actually dry quite a bit more than what we are showing here. But based on our particular boiler design that exists today, our optimal level is to get down in the 28 to 27% moisture level. Now, with modifications of our boiler, we could dry more, and you know that is a further consideration for us for further CO2 reductions. But so anyway, you can see here how the moisture has dropped. And then if you want to go to the next slide. So because we're not burning a lot of coal to drive the moisture off, we're burning less coal because the coal is drier, the energy density of the coal gets quite a bit more. So it's got less moisture in it, and as a result, the BTU content goes up. So you can see here where we raised our BTU content from around 6,200 up to around 7,100, 7,200. And we're currently in the process of slowly moving that level up some more as we further refine the system. Okay, next slide. So this is an important slide here. You can see that red line off to the left is when we put the thing in operation. Over the next several months we tuned it, but what you're seeing here is a graph of how much fuel was burned, how much coal, and relate that to CO2 for the megawatts produced. Hence the idea of lowering your carbon intensity for the amount of megawatts that you're producing. Next slide. I'm not going to dwell on this slide. This is just some test data, particularly right after we came up. But this this drying process, because you're burning less coal, you have less flue gas, or less gas coming in, air that you're sucking in for combustion. And as a result of that, you lower NOx, because NOx is directly related to the amount of air that you put in the boiler and the heat that it operates at. It has less wear on everything going through the system, all of your ductwork, your mill operation. We went from 8 mills running on each unit to 6 mills running on each unit. So the cost for running the mills and maintaining the mills is quite a bit less. The cost for the electrostatic precipitator, or in case if you had a fabric filter, you have less volume going through that, less velocity, so they are a lot more efficient. So our particulate improvement was there quite a bit higher. Because you're taking out some of the sulfur ahead of time and you're scrubbing less, your SO2 goes down, and so all around you're requiring less station services to run the fans and the mills and other things. So as a result of that, the plant is more efficient. So all the way through, there's all these benefits. And in our case, early on, we showed about a 3.5% heat rate improvement as a result of this. And translate that to carbon intensity, if you will. And depending on the design of the plant, you can do, like one of the plants we've just evaluated can do better than that. One's a little bit less than that, but it's a significant benefactor for all of these different emission sources, as well as for your operations and maintenance costs, which goes to members' affordability of the rates of the power coming out of here. Next slide. So this is actual data which we've updated here recently based on almost 6 years of operating experience. The net savings per ton of coal for us is about $2.76. This is a significant number for us because we have very low cost coal because we have a mine mouth plant. And for those, so anyway, this has a significant amount of benefit. And you can see kind of a little bit of the breakdown where the savings come from. And then also the red there is where there's some additional costs. We require, as more equipment we have a few more operators and such that we've hired, and a little bit of maintenance. And then there is a little bit of power required to run the system. But the green is the net overall operational savings for us on an annual basis, or, well, in our O&M savings for running that. Next slide. This is a very compelling reason for doing what we did. Back in 2006, when we got our board to approve this, we showed them what would be the cost to us if we had to put on conventional emission equipment. And this is before anything having to do, this doesn't even factor into account, carbon dioxide. But in each case, we had to spend some money on capital equipment to go ahead and get what we needed. But in the case of dry finding, which is that blue line, we recover those costs through operational savings. And so basically, this is an emissions control technology that pays for itself. And then you can see, in the case of conventional equipment, SNCRs, additional scrubber modules or reagents that go along with it, mercury, activated carbon control, that you continue to pay for that and pay for that and pay for that. And it doesn't, it's an expense to you that you don't really get back. Okay, next slide. Now, there's other things that has made this very attractive for us that we've taken advantage of. And this picture you see here is a loadout facility we built on Coal Creek Station to actually dry additional coal at Coal Creek using dry finding. And then what we do is we load it out to covered rail cars, and we are shipping it to a new plant we just opened down about 170 miles away, Spiritwood Station. So basically, we're taking this heat from this plant drying the coal, shipping it by rail. Because it is dried now, we're not shipping a bunch of water. So this was a better option for us than using Powder River Basin coal. We ship it down to this plant, which is a combined heat and power plant, which is being encouraged. Has a very low carbon footprint for a fossil plant, and we are supplying electricity and steam from that plant to a couple of one ethanol plant, and one is a Cargill malting plant, and it has room for some additional heat customers on that. So, and now this is kind of important because in China, we're been talking with them, they're very much concerned about actually shipping dried coal to other areas, and so by not having to ship water, it really reduces the freight costs also. Next slide. So I'm going to talk a little bit about, I'm going to circle back to where I was at the beginning, where we talked about the China and overseas market, where there are many new coal-fired power plants being built, on the board, being planned, and currently being developed. And in China, for example, where they have all this, a lot of the heavy manufacturing capability has left the United States. It is located in places like China, especially China, and they are bidding on and designing plants for other countries in addition to doing what they're doing internally in the country. And so, the reason they're doing this is the developing world wants the kind of life that we have, which is to say that they want in order to advance, they need to have affordable and low-cost energy, and coal is, whether we like it or not, it is an abundant, low-cost energy source, and that's where they're turning to. And much of this coal that they're using is low-rank coal, about half of it is. So dry finding really has a very strong possibility for what we're going to see overseas as far as helping them out, reduce their emissions and their carbon, as well as reducing their costs of them being able to actually build power plants. Next slide. Now, I'm going to touch on China because we've been over there several times. We actually have an agreement, and we currently have a number of Chinese companies, large utilities. These are utilities that might have 120, 140 gigawatts of power, and they are looking at their fleet, and they are looking at this technology as a way of helping them out. And you can see on this particular drawing here, or graph, generally the population is in the east part of the country, but you can see where the coal reserves are. And particularly up in the Inner Mongolia area in the Xinjiang province, which is out in the west, is where you have lignite, and as well as you have bituminous coal. So what China is doing right now is they're trying to locate these plants outside of the populated areas. So like Beijing, which has such a problem, a lot of it through their automobiles, but it's kind of their region. They have mountains not too far away, and there's certain times a year they just have tremendous problems with particulate and ozone and other issues with their heavy population. So they're actually banning new construction within a 200-kilometer radius of some of their largest cities. But what they're doing instead is they're locating them out in these outer regions, and they'll be, running the power by DC line and other means, or shipping the coal from these areas. So they have two main imperatives in China. One of them is they're looking to dry the coal, so they're looking very heavily at our technology, and then also they're looking to recover the water that would come from drying that coal, because this lignite is located in very dry regions where they have water problems. And looking at the top graph there, you can see how much more coal is being used in China, and India is approaching what the US currently does. And then you have other countries such as Indonesia that are really on the rise. Pakistan wants to put in things. And so Turkey right now is looking at building coal plants and is actually going out for bid. So you can see right now this is a worldwide thing that we are dealing with. And China is now actually, despite their fact that they mine much more coal than we do in the United States, they're actually an importer of coal now. And anyway, just wanted to emphasize that, because to have the discussion of what's going on in the U.S. and ignore the rest of the world doesn't help anything. So anyway, let me move on.
Dave, we got about probably about 5-6 minutes left for talking. So, and I know you've got a few more slides.
Okay, I'll be almost done here. I've got the reduction of capital costs on these new plants. You can see by sizing the equipment, depending on how low the BTU content is. By sizing the equipment less or smaller, you can build smaller boilers, scrubbers, etc. So the actual capital costs decrease for these plants, and this is what's very appealing on new plants being built by incorporating dry fining. Next slide. So basically, just kind of in a nutshell, on as far as a new plant goes, you reduce the size and components while you also lower the emissions. This is very appealing for these new plants being built. Next slide. This is U.S. costs here. This is about what a cost for two 660 megawatt units are in U.S. dollars. This is if you were building the core equipment in the United States. Overseas, they can cut this in half, basically, with their ability, with their lower labor costs and lower material costs. And this does not include any foundation or conveyor work. That's going to be very site specific. Next slide. Just to mention that in 2010, we received the Project of the Year Award by Power Engineering. And we have 9 U.S. patents on this. This is a commercial technology that we've been running since that time. Next slide. So just kind of summarizing, this is a technology that can help the states. This is not a silver bullet, as Miles mentioned earlier, but it could definitely help toward meeting some of the energy and environmental goals. Allows you to retain some of this baseload generation, which is really important. In a world filled with renewables, baseload becomes very, very valuable. And then it reduces the carbon footprint and does a great deal toward helping out on the regulated pollutants that we have out there, and it helps keep customer rates affordable. So anyway, that's kind of it, and it definitely has an impact in possibilities for the worldwide burning of coal, low-rank coal. And with that, I think I'm done. And I think.
Dave, yeah, that's it. I'll make folks have availability of your contact info in just a sec. We do have a few questions, and we got about 10 minutes to dig through them. Folks, if you have questions, we do this the same way every time. So I'll just mention again, you can enter in questions in the questions function that's over to the right of your screen there in your webcast software. And if you enter them on in, I'll go ahead and read them out. I want to start with a few questions. One was one that someone texted me that asked, David, for the addition of dry fining, are there any kind of capital savings that you get by putting it into the design from the get-go so that it would be a little cheaper to do on new facilities instead of facilities that are under?
Yes, that was that one. Yes, that was that one graph toward the end on a new facility. The lower rank the coal is, the more that savings is because of how you can size the equipment. So per the, I believe that was the EPRI research, they were showing with low rank coal, you might get a 10% reduction. So let's say you have a plant that costs $1 billion, you might be able to save upwards of $100 million on the capital cost. And it's, the higher rank the coal is, the less that is, but there's still an improvement. And we had an independent research on that showed some, kind of validated that. Maybe not, it wasn't quite as high as EPRI's, but it did validate that.
That's fantastic. Gary Garrett, my friend from the Southern States Energy Board, a longtime friend of Ice Picks, and always throws out great questions. His is, does this work on a wide range of low coal rank types? Are there some low coal rank types that it works better on than others? How does this apply to different kinds of lower rank coals?
Well, it will work. It works from the standpoint of moisture reduction and efficiency. It works depending on your moisture level that you're drying to and how much. So it doesn't matter really what type. It all depends on how much you're trying to dry and what level you're trying to dry to. So it works across the boards. Now, where there's some variability is, say, on the SO2 and some of the other savings. That will be somewhat dependent upon how much pyritic sulfur you have and other variations within the coal. I will say, too, that a plant that is very close to their design efficiency will see less benefit on the efficiency than if you're off from that. Now, what's happened is many plants have gone ahead and their boiler doesn't operate anything like it was originally designed. It's not maximizing its performance because of changes they've made on it, because of emissions equipment and other things. So usually you can realize a good benefit there, but there's some plants that might be really close to operating at optimal efficiency on their boiler where they wouldn't get quite as much of a benefit.
David, that's super interesting. Cindy Holmberg from New Mexico's commission has an amazing question that was making me scratch my head too. You identified a bunch of different kinds of emissions characteristics improvement, and you just mentioned sulfur ahead of time. Dry finding is effectively a process that's applying a little bit of waste heat to the coal and reducing its moisture content. How does that help lower the amount of sulfur that's in there? Does it remove sulfur with the moisture ahead of time?
Right. There's two things that are going on there. What's going on is that, first of all, we have mechanical separation right at the front end that will remove a lot of the heavier elements that will contain both pyritic sulfur as well as mercury and other bad actors. So you're removing a little bit on the front end. So think of it this way: you're getting it out of there before it even goes through the boiler, so you don't have to treat it later. But also what happens is, because you're burning less coal, you're injecting less air into the system, and as a result of that, you have your scrubbers work better, the dynamics of them, you're not pushing as much air through that has to be treated, and as a result of that, you're able to get significant SO2 significant lowering. NOx is an interesting one because NOx doesn't have anything to do with anything we're removing. What it does do, though, is we have to put less coal in the boiler and we have to put less air in the boiler, and as a result of that, the NOx lowers down from what it had been before. So we did not have to install SCRs, for example, because this was our control technology.
Outstanding. Maria Zacera asked a question which I've been trying to scroll through your slides and find exactly the one that answers this succinctly. And maybe you can just answer it succinctly while I'm busy scanning around to find the answer. What in the end was the heat rate improvement that you got out of doing dry finding on Coal Creek? What did you start at and what have you been seeing? And is what I'm showing now energy density?
Yeah, that's what you're seeing there. Now that's the heat content, but from a efficiency standpoint, it was about 3.5%, and we're creeping up on that a little bit higher as we continue to drive the system a little bit more and make other improvements on the system. And that will vary from plant to plant. Depending, we're analyzing another couple sites right now, and one of their plants, they can get a 2.5% improvement by our calculations. Another one can get a 4%. So it will vary somewhat depending on your heat sources and where you can pull them from, and there's other variants to it. But, you know, generally that 2 to 5% range is what we're seeing generally as we've looked at other plants.
You've mentioned that you're going to ship some of the processed coal down to Spiritwood. Does Great River have any intention to apply the technology or this approach to any of the other facilities, or it's built here, you pull the coal off the pile and process it through some dry fining, and then you can take it other places without needing to re-implement the stuff on other sites? Or are you just, you're trying it out at Coal Creek and seeing how it goes?
Well, right now we are currently using it at Spiritwood, so we're using it at those two facilities. We have one other facility, Stanton Station, which we're evaluating now. A little bit of complication there, our compliance strategy, which with the regional haze rule, we have to comply by 2017. That was built upon a Powder River Basin as the fuel source. So we're kind of sifting through that, how best to and what to do, and it's a smaller plant. As far as retrofitting it, it's about 180 megawatts. So, we're still looking at that one, but that one has potential. But we are looking at some of our neighbor plants, and actually we'll be meeting with some of them here within the month to start talking about potential for retrofitting their facilities.
That's awesome.
And then we have Canadian and other U.S. Utilities that have contacted us also. And we've tested their coal to understand the characteristics and know that, basically how much we can get out on the segregation process.
That's fantastic. David, I want to really thank you for coming on with us today. Friends, I think that this is an important entrant in the marketplace of ideas about what do we do with some of our coal plants. I know we did things a little differently today than we've done before. Usually we have a couple speakers, we bounce around things that are a little less technical than this, but my mind was so blown by some of the implications of this, no parasitic load, lots of other stuff that goes on that makes this really appealing, that I thought that David, that his presentation deserved a broader audience, and so we just have the one today. I hope that you will join me in thanking David Farnsworth for a really amazing presentation today, and I've put up his contact information here. I know he is, given my own personal experience interacting with the guy, he's willing to answer questions and give you the insight of his smarts, of which there are a lot. Thanks again, David, for spending some time with us. For those of y'all who are wondering what it is that we're going to be doing with our next Brown Bag broadcast, next week, on the 13th, which is a Thursday, NARUC is going to be doing a big clean power plan presentation in which the bigwigs from the EPA will be coming and walking us through a bunch of questions that NARUC posed to them in the final days of the preparation of the final rule. And they're going to show us what the final rule looks like. They'll skip the summary that they've done on everybody else's webcasts and really focus on answering NARUC's questions. I think it's going to be amazing. We're going to be doing a bunch of other other broadcasts next week. So next Friday, we're not doing one of these. We're giving you a break. I hope you'll use that time with something reckless and foolish, and don't try to learn anything. We'll be stuffing your brains full of lots of other inputs from the marketplace of ideas throughout the week. But on August 21st, come on back. We'll have Tom Sloan, representative in the Kansas State House, who's absolutely brilliant, and some folks from AEP talking about some transmission line designs that may help us through technology lessen some of the difficulty of siting and cost allocation problems that we face with interstate transmission lines. Maybe, maybe not. If you're wondering how that could possibly be possible, all I can say is we'll see you on August 21st. With that, thanks again to David and to Great River Energy for coming and spending time with us. And I'm going to go ahead and end the webcast. You don't have to go home, but you can't sleep here. Thanks, y'all.
Thank you. Thank you.